Copernicus Astronomical Center, and she will tell us about the dark energy and quasars.
Thank you very much for the invitation. I'm here for the first time. In such a short occasion, and I will be happy to present one of the projects I currently work on, which is partially financed by the Foundation for Polish Science. You see, it involves quasars and dark energy idea, and quasars are kind of my speciality. On the other hand, dark energy was not, but it's a quite fashionable problem nowadays. I think it's one of the biggest puzzles in cosmology and in physics. So why not to try to join those two things? And my list of collaborators is quite long because the project is quite complicated, as you will see. So first I should tell you what the dark energy is. Right, well, it's easier to say what's not. This is not dark energy.
Except of this left column, which is pretty dark.
Well, our solar system also is not dark energy and does not contain significant amount of dark energy. Even galaxies, they do not contain dark energy in a sense. So here you see Milky Way, here you see the Andromeda galaxy, and a collection, very nice collection from Hubble Ultra Deep Field. This is not yet an example of dark energy. On the other hand, they do have dark matter. And I like very much the illustration of the dark matter here. So all usual galaxies sits inside the halo of dark matter.
Yeah, but since according to the relativity theory, the energy and mass are essentially identical.
No, not dark matter and dark energy.
Yeah,
They are
that
not
was not the question. So how do I distinguish between dark matter?
Wait.
Well, this is exactly why I show this picture. We know that dark matter is something which forms clumps. It can be self-gravitating. So those clumps are self-gravitating, and the dark matter here dominates the overall gravity and provides the gravitational confinement for the matter which is here. This is especially true for galaxy clusters. Without that, galaxy clusters would not be bound. But dark energy is something different. So I will not tell any more on dark matter. I will concentrate on dark energy. So still not saying what it is, I show you the current idea.
Honestly, it's not sufficient explanation for me. I don't understand the
So,
difference.
so this is why I will
what
do
you
the
said is
project.
that the dark matter is something mysterious thing which we don't see, which is there because otherwise something wouldn't work.
Yeah.
Now, of course, we are bringing up the problem of a dark energy,
Yeah,
which
is
is
even more.
supposed to be distinct from the dark
Yes.
mass, but then what's the
It has
distinction?
the opposite side.
Yes.
Yeah, but that wasn't said.
Yes, but
Yes.
wait for the rest of the lecture. You will learn about that.
I would like to have the definition.
No, there's no definition.
Oh,
Yeah.
that is the
Yeah.
answer.
Yeah, the answer is we don't know. So if I, in that sense, start with the lecture
But I
and instead
understand
of
that the
finishing,
title quasar is
I'm
a
not
lot of something we
going-
don't know is not really
well,
good.
That's why it's
I will try to measure it, this thing which we don't know and don't understand. And this will kind of open the way for interpretation. well-known baryonic matter. And then most of this baryonic matter is actually in the form of gas. Only small part is in the form of stars and a fraction in the form of neutrinos. But indeed, 95% of the universe as we know it now, or as we suspect it's true, consists of dark matter, which is hard to understand, and this dark energy, which is impossible to understand. Right, so this is really a problem and a crisis, but...
Yeah, but it seems that experimental evidence for dark matter is much stronger
Yeah,
Yes, of course.
yeah, it is
than
much
for
stronger.
the dark energy. So
It is much stronger. That's right. And theoretical understanding, I think it's more advanced, because then many people suspect it's kind of weakly interacting into massive particles or WIMPs or neutralinos or whatever.
I'm terribly
Wow.
sorry. I was told that the dark matter is something which keeps this rest of the universe in a shape.
Yes.
Yeah,
Okay, so
it's clamping.
what is the supposedly experimental evidence of the dark energy? How did concept came about?
Expansion of the universe.
I will tell you
Wait a second, wait a
I will
second.
tell you that because the aim of the project I do is not to provide a theory for dark energy. It's to provide the means to measure it or to measure the problem. Exactly. So how we see this situation observationally? This dark energy seems, but of course we have still to confirm it, feel uniformly the universe. So this is not this clumpy medium. This is something which is very uniform. Then it has negative pressure. Dark mass has zero pressure, basically. It causes the accelerated expansion of the universe, so it acts as anti-gravity instead of gravity. And for the moment it looks like it behaves like cosmological constant of Albert Einstein.
Why is it not just the cosmological constant that behaves like it?
Because you put it on the right-hand side of the
For
equation.
public relations, it's better to call it dark energy.
So it's not better.
Cosmological concept.
It's not better to put it on the right-hand
Perhaps
side
for
of the
something
equation.
more general, perhaps for the moment all measurements are exactly consistent with cosmological constant. If we do the measurements 100 times more accurate, it will be cosmological constant. It will be kind of proof. On the other hand, we
Geometrical
can think
property
more
of a space and time.
Yeah.
Yeah,
But if you put it on the right-hand side of the
Yes.
equation, then
Yeah. Yeah.
but
of course.
But if I write it upside down,
But that's negative side.
hopefully,
The physical problem which we see is this kind of acceleration of the expansion of the universe, and indeed many people worry that perhaps we are making some mistake or whatever, because this accelerated expansion started at the moment when we actually start the measurement based on large-scale structure. So some people say, well, it's a mistake, it's a kind of non-uniform Big Bang or something else. So there are even alternative suggestions. It's not that everybody agrees that we have just the cosmological constant, we are happy and we solve the problem. So what we need is really the exact measurements of the expansion of the
but
universe.
there's another thing which, I'm sorry for asking the question, but the structure of the semiconductor is that even such a complete idiots like me are permitted to ask the question. You said that the dark matter has zero pressure.
Dark matter,
Yeah, well,
for the matter.
how come on the physical grounds, if I have a physical object,
If
it
it is
consists
very
of
cold,
something?
it has very low temperature. Pressure is related
Yeah, but
to the temperature.
that's just the question that the equation of state is wrong. If you, because I mean, there is no reason why the matter, even as I mean, a piece of metal cooled to 0 temperature also has a finite pressure, although
But it's more like gas, right?
well, the electrons. I mean, the
If
magnetic
you
moments. There are many
if you
magnetic
pull
systems when we're
electrons-
cooled close to very low temperature.
If you put electrons to very low temperature, they will have low pressure. And because in astronomy
But I
we do
can
not...
cool the magnetic system to
But
0
with
temperature.
electrons, that's not really true, because finally quantum
Quantum
aspects will
effects.
appear. The
Yeah.
fermions cannot be squeezed.
But
Squeezing, there is a pressure, I mean,
Well,
even at the temperature
I'm
exactly
not
0.
saying zero in the absolute term. I mean in the sense of the accuracy of astronomical measurements. And the
There are
accuracy of
completely different
astronomical
densities and completely different length scales.
are very bad. So at least what I can tell about the dark matter,
No, the
which
question is
not-
that if the
it's
full rule of
lower
this,
than the pressure of the gas, which has usually temperature. For example, in the galaxy cluster, the temperature of the gas is 10 to 8 kelvins, and this provides kind of pressure.
the only
Dark
reason why I
matter,
ask
in
is
comparison
that
with that, is low.
it's easy.
How low it is? I
It is
cannot
easy to construct a relativistic system for which the pressure will be proportional to the metric tensor G, and it will have a certain coefficient in front of it, so it would be appearing on the, as you said, on the right side of this equation in exactly that form.
Yes.
So so maybe this lambda, I mean, the question is, why do we divide something into dark matter and dark energy? I don't
Because
understand.
it's completely different.
Because
It's
the
nothing-
dynamics
Well, I
of
just
unknown
gave an example. I can concocte a system for which the pressure tensor is equal exactly to something times G.
Then write a paper about it, but that's not the
But
subject of this
it
seminar.
has been written hundreds of years ago by
So-
Hitler. The relativistic gas
So
can
let's-
exist.
Subject
say-
is dark energy.
let's say in this
not
way.
go back to-
We have two problems to solve, really, in astronomy. The first problem is to confine galaxy clusters. And the second problem is to explain the accelerated expansion of the universe. This requires larger gravity. This requires lower gravity. We do not know the answer to those questions, and we hide our lack of understanding, giving a name of dark matter here and dark energy here. But we need two names because we have two puzzles and they require different approach. And that's probably the most honest, immediate answer I can give, and I will not give any other actually. I will just try to measure what I need for the second part, observation.
Can I add a remark? There's another difference between the two, quite important, namely, dark matter is known to be spatially localized. It exists in some places, but not in other ones.
Yeah, this
is
is
not
one.
true
This
about
is
dark
just
energy.
one of the examples because I didn't want to complicate the things. There is rotation curves in galaxies, etc., etc. Long lists, but within this part. Yes, I agree. So, of course, we now want to see where this dark energy is, and we want to measure it. So the only way which is possible for us is to use the kind of detective work. And the second practical issue, we we have to look where it's bright, right? Jasno jest pod latarnią. Tam szukamy. In Polish. Because we are not going to find anything in the places where it's dark. So here I will outline the way how we measure the expansion of the universe. So let's assume we have an object at certain distance. And to measure the expansion of the universe, we want to measure the distance to this object and the velocity. So we have to measure those two things independently. And this is how the expansion of the universe was actually discovered. This is the Hubble diagram from the original paper of Hubble, where he measured the distance and the velocity, and he had few measurements, and well, they did not yet look very convincing at the time of publication, but still that was the beginning of the measurement of the expansion of the universe. Now, a most known way to measure the expansion of the universe is to use supernovae 1A. And the idea is, again, similar. The only difference is that in the meantime we change the axis from the original approach. So if people studying supernovae 1A usually put here redshift and here the luminosity distance. So the luminosity distance is the analog of the distance, and the redshift is just the measurement of the velocity, because the Doppler change is easy to measure, and accuracy of the measurement of the redshift is always very high. This is not a problem. For a given object, you can measure the redshift with accuracy 10 to minus 5, for example. The big issue is to measure the luminosity distance. So the general definition of the luminosity distance is that it is the intrinsic or absolute luminosity divided by 4 pi and the observed luminosity. Observed luminosity of an object is square root of that. Observed luminosity is something which is measured with the telescope. Again, it's not a problem. But we have to measure the intrinsic absolute luminosity, not going there. And this is always the largest problem in cosmology, how to measure. In the case of supernovae 1A, the idea is that they are all identical. So if we see the observed plans, from the fact that they are identical and we know how they should look like, this is this figure, we can determine the absolute luminosity. Of course, the idea of standard candle is easy, but the practice is quite complicated. You have to do quite a lot of shifting and stretching actually. So it's important to have whole light curve, and then you have to apply several coefficients of pushing it this way and that way, as you see here. And then you think you derived your absolute luminosity, and if you have your absolute luminosity, then you can measure the luminosity distance, and then you can create the plot which I showed before.
So what do they assume? They assume that they have essentially the same mass, and essentially entire mass is just
yes, that's right.
transformed into energy?
Yes, but there are still some corrections.
As far as I remember, a story of Jose Maria, who was one of the guys who contributed to this program many years ago when CCD detectors were discovered or introduced into astronomy of measuring distant supernovae. We say that they are all alike, but they are not all alike. They brightness depend on the environment, they somehow explode and so on and so on. So there is a lot of, before they became standard candles, now historically we teach students that they are standard candles. Before they became standard candles, there was a huge effort and arm wrestling to understand why, although they should be standard candles, they don't look like, and you know, calibrating those curves until all of them really follow exactly the same line. This is
Yeah, so
quite
this is not,
fascinating.
this is before, the range of possibilities before calibration, and then you have to shift everything to an
Yeah, and then
average.
Jose Maria showed
Taking
me
into
a
account
paper when all those
those
curves were
connected
just
with the time scale. So
modeled in such a
we
way
used this
that they fit one single curve.
Yes.
And this is the standard
So
curve.
there is always a lot of dirty work, and then there is a difference whether they sit in spiral galaxies or elliptical galaxies, and well, so. But okay, it's
If this
general.
is such a difficult job to get this scale,
So this is why some people.
why do we use this? Is there any other definition of DL or
No, the answer is no. And this was so excellent that the Nobel Prize was given for that, right? We don't have, I will propose quasars, but, well, then you will say that they are not that excellent as well, okay?
By the way, again from the same source, Jose Maria, when they started it, nobody believed in this research program. So today they wouldn't get any grants.
Nobody believes that it's true.
No, that this is doable and so on and so on. They got the new technology, CCD technology, they could perform much more precise observations than before, and they decided to attack the most difficult problem of the universe, so to speak. So supernovae in distant galaxies in order to follow the expansion. This was the most ambitious project you could imagine at the time, as most astronomers set for a much less ambitious project, variable stars and so on, binary system, etc., etc. And nobody believed that they would succeed, but they did.
Brian Schmidt was telling that they were checking for about half a year the sign. They thought that they made a sign error in lambda because it was supposed the other sign, to have the other sign.
Many, many years later, somehow, when they completed the sample.
Yes, so because the measurement is quite complicated, it's better to have more probes, and there are other probes suggested, and I propose one more probe, namely quasars. So now I will say a few words about quasars. Quasars are central parts of galaxies. So here this picture covers more or less 1% of the whole galaxy. So whole galaxy is around. Inside the galaxy there is a supermassive black hole. There is an accretion disk and the dusty molecular torus and some clouds which emit emission lines. So you can have a jet or you can have radio-quiet sources without a jet. So the structure of the quasar indeed is more complicated than of a supernova because it's not spherically symmetric. You have only axial symmetry. But still we have some understanding of this quasar structure. This is the idea which comes back to 1995. And quasars are numerals. Not all galaxies are quasars. Our Milky Way is only weakly active, but there are numerous quasars, and they are very bright. So we can consider using them as well. They are numerals. We now know about 100,000 quasars. 500,000 quasars will come from Gaia, more will come from other
there's
searches.
one quasar per one galaxy?
Yes.
Or less.
In our galaxy there is no
Statistically,
quasar.
it's 10 to minus 6.
Yeah.
Statistically, it's 10 to minus 6 because not every galaxy
There's a quasar, right?
is a quasar. And first of all, you need a very high black hole mass to have a quasar, something like 10 to 8. If you have 10 to 6, then it will be moderate source, not big quasar. Although there is no, it's a semantic difference whether you have active galaxy or quasar. Quasars are just by definition bright. It's like definition of tall people. You set somewhere the limit and then you call people tall and they are higher than something. But still, they are numerous, and from future surveys, we will have few millions of quasars, no problem. And quasars can be seen up to redshift 7. So, and this large redshift is not so easily accessible from for supernova 1A. And what is also interesting, they do not show significant evolution with redshift in their properties. Or technically, their metallicity is roughly the same, because somehow the star forming activity and quasar activity, they are correlated in such a way that they are always of more or less solar metallicity. So we can try to use them. But of course, they are not standard candles. They differ in luminosity by orders of magnitude. However, what I propose is to determine the absolute luminosity with high accuracy for a given quasar. For that, I need still a few more informations. So we observe quasars mostly in the optical band, of course. We can do in other bands as well. And there we see the continuum, which comes from the accretion disk close to the black hole. And on the top of the continuum, we see broad emission lines. Those broad emission lines come from the region farther away from the central part, where most of the energy is dissipated and this continuum is produced. So there is some delay between the lines, which are produced by irradiation, and the continuum. And those continuum and lines are variable, so we can measure this delay. And this delay can be measured quite accurately. And now we explained in this paper with my previous PhD student how this delay can be translated to the absolute luminosity of the quasar. And the idea is very simple. I try to advertise it, but frequently I meet with the view that it's too simple and then it's impossible. But it's just that somehow nobody noticed something which is obvious and could have been known since many years, was just not noticed. How the situation looks like close to the black hole. Here you see the same thing, but in a kind of simplified cross-section. You have an accretion disk, you have the flow of the matter close to the black hole. And of course you have high temperature close to the black hole, in deep potential level, and lower temperature farther out. And at some point, the temperature drops below 1000 kelvins. And in astrophysics, this 1000 kelvins is essential because that is the sublimation temperature. And if you have a lot of dust, you have a lot of wind because your radiation pressure is acting very efficiently. And this we know from all stars. If you have dust in the stellar envelope, you have a lot of wind. And that explains very easily why the matter from the disk is taken up, because this was never explained. Why those clouds, which are nicely irradiated, are well above the accretion disk. And on the other hand, we have from the shape of the lines, we know that it's not a kind of wind. And our picture explains that, because if we have those clouds which go up due to the radiation pressure, then they are irradiated by the central part. This irradiation causes the dust to disappear. Radiation pressure decreases and the material falls back onto the disk. So those clouds are just jumping. It's not an outflow, it's a kind of jumping clouds. And it all starts at 1000 kelvins, independent of two typical parameters of the black hole, mass and accretion rate. I mean, not black hole, but the whole setup, mass and accretion rate. We have just one number.
Does this oscillation have a characteristic frequency?
Well, it has Keplerian frequency locally at a given radius. But of course, it depends on the radius, so the small motion is slower here, faster here. So we first we call this scenario FRADO, fate radiatively accelerated dusty outflow. And it's nice to name because FRADO means also something ugly, dirty, and because it's a dusty outflow, I think the name fits. Now the question is how we translate this into the absolute luminosity, and this is why I really don't know why people didn't notice. I show you those equations just because I want to tell you it's not that I invented this thing as just hand waving. If you use simple equations which were published by Shakura and Sunyaev in 1973, which means many years ago, and you do some algebra, if you use the value of the effective temperature, and you calculate the effective, and you calculate the radius where this effective temperature is located, all depends on the product of mass and accretion rate. And the monochromatic luminosity which you measure also depends on the product of mass and accretion rate. So for any mass and accretion rate, you have the direct relation between the radius, where this starts to happen, and the absolute luminosity, square root of absolute luminosity. So if you measure the radius or the time delay of the lines with respect to the continuum, you measure the absolute luminosity. And that's it. And only you have to choose the suitable lines for that. For nearby objects, H beta is good. For intermediate objects, intermediate redshift quasars, magnesium, and for higher redshift carbon 4, but I don't want to talk more about that. And actually this kind of delay measurement was performed for nearby objects, and this relation with square root was seen in about 40 nearby AGMs, and it was a puzzle for a long time why this relation between the radius and the luminosity shows very little dispersion, and the scaling is not with the ionizing flux, which is different in different sources, and just with monochromatic flux. So our theory just explains why we see this kind of relation for nearby objects and allow to use the same relation for more distant objects. So we started observational campaign using a SOLT telescope, Southern African Large Telescope, with the aim to monitor intermediate redshift quasars, just to see what is the accuracy, whether we can reach the same accuracy as for the supernova 1A is possible. And we do this. Well, it's quite a big telescope, 10 or 11 meters, depend how you measure it. Of course, there is some kind of dirty astrophysics there, because in order to measure the line emission, you have to do the decomposition of the spectrum. This is the magnesium 2 line. So here is the continuum, here is this magnesium 2 line, but here there is some iron emission which we have to subtract. So there is some technical work as well. But still, we estimate that we can measure the line with the accuracy of about 10%. We now monitor those sources for 15 months, so it's not yet long enough to determine the delay. Because, well, this delay should be of order of 300, 500 days. So we cannot yet tell the delay. We did some Monte Carlo experiments, purely theoretical, interesting units which supernova 1A people use. So we will have more or less the same accuracy if we keep this accuracy right, hopefully. And our monitoring is proceeding nicely. So we have 5 photometric measurements. We have spectroscopic measurements of the MG2 line, and photometry. We have photometry from ODL team. Publicly available photometry was not really useful, and we have to wait longer to identify perhaps this peak with this what we had here. We have just to wait longer. So in the meantime, we can also try to test our theory, develop it further, and see additional arguments that the basic theory is working, and we can then better estimate the systematic errors, because the key always in every method is the systematic error problem. So we are still working on that, but we see already one interesting result from our theory. This kind of jumping up and down of clouds can be shown that it proceeds with the locally Keplerian speed, as I said. However, the height is always the same in absolute units. So if you look at the viewing angle, then all irradiation is actually intercepted here in this part, and not that much in this part. So probably we will prove in this way, I wouldn't say yet that, but probably, that this kind of dusty molecular torus I shown at the beginning does not exist. And actually any outflow, if it happens here. So it's kind of whole, well, strange geometry, but not a torus which is known not to be possible to keep in hydrostatic equilibrium. That's I think too technical. So we are also doing some kind of theory, because waiting just 5 years more for new data would be kind of boring. And of course we look for other possibilities to get more data, because with SOLT telescope we can monitor only 3 quasars. So this is a kind of laboratory to test the accuracy of the method. But we are in contact with Chinese people who have a LAMOS telescope, which is for surveys. So they have 4-meter telescope. Lower accuracy can be achieved, something like 6 to 10% in the line measurement instead of 2% in SOLT. But they can have thousands of quasars. They measured already few thousand of quasars, but for the moment they stopped monitoring and they started to do more stars than quasars. But I hope I will try to convince them not to do what everybody is doing or what actually Gaia is doing. They want to match Gaia project instead of doing something which is parallel. Well, I don't know. Then there will be in 10 years or so excellent project, Large Synoptic Sky Survey, which will bring many supernovae, but also many quasars, like about 1 million or 2 million of quasars. The problem is it's photometry, not spectroscopy. So then instead of measuring, separating the line and continuum, I will have, let's say, a broadband which is not contaminated by the line, and band which is contaminated, and we are still working on the issue what kind of accuracy of the measurement we can have from such setup. So I cannot yet tell you whether it's viable or not to use this, but I hope it is. There are also other ideas how to use quasars instead of the one which is based on the time delay of lines with respect to the continuum. One method is to select quasars which are really identical, let's say, which is kind of risky. I would have to enter into many details to explain why it's difficult, but it is difficult. The line shape or other signatures do not measure you well the Eddington ratio, and the normal dispersion Eddington ratio is 2 orders of magnitude. There is also another idea, doing reverberation by the dusty tolls. So measuring the delay not from the clouds, but from the dust which sits farther out. That involves less theory, so that's the advantage. The disadvantage is that this delay is much longer, factor of 5 more. So if I expect 5 years delay in quasars, it's 25 years for dust. Well, in astronomy it's possible, but you have to be more patient. So I don't yet have final results, but just as an exercise, I tried to locate on the standard supernova diagram 2 quasars where perhaps we can have some idea about the delay. So this is the diagram for supernova, and it's easier to see the situation on the bottom part, where we measure the excess of the distance in comparison to the constant, cosmological constant prediction. And supernovae are just consistent with the cosmological constant. There is one quasar which was monitored before, it's not our work. It was completed in 2007 by Kaspi with similar telescope head. They monitored several objects, but only for one they determined something they called tentative time delay. They were very careful. They were working with carbon-4 line, and that's a big problem. But they determine some delay. So I can translate this delay to this delta mu, which is here, and this is this quasar. If I think that our quasar already is at the edge of the time delay being measured, but I cannot be yet sure, then our source would be here. So those two are for the moment above the constant, but I wouldn't draw any conclusion from our measurements because it does not yet, it's not a real measurement, and this also is not a real measurement, it's tentative measurement. But it looks promising. I think we should continue and try to construct similar diagram for quasars. And there is the short summary. So I didn't try to answer what is the dark energy. I first tried to measure it accurately because I hope that if it shows some features, like for example, dependence on the direction, or stranger, more complicated behavior in the past, this will perhaps help, because if we just face cosmological constant, then we cannot do more than just say, oh well, yes, Einstein was right. And the number of the quasars should increase, and there are surveys which will be or can be used in the future for this. And I think it's really essential to have sources which are treated in a similar way as supernova 1A, but they go to higher redshift and probably with lower systematic errors, I believe. At least I would be really, really happy to see whether the two give the consistent result or inconsistent. Both results, I think, would be really important. And thank you very much for your attention.
Could you explain this problem, essential problem of time delay? to have a time delay, there must be some clock that you can measure. It's not a continuous process that you observe.
Oh, well, it's practically. I'm not sure if I understand your question, but what I do, I have spectrum,
Yes.
line and continuum, spectrum 1, and then 2 months later, I have spectrum 2. Continuum is higher and line is larger. So I measure independently line and continuum. And I have 2 light curves, and the time which is here is my laboratory time. Knowing the redshift, I can change it to the rest frame time.
Yes, that I understand. So the
So I
process
have,
is
let's say, a line, and then a continuum like this. If I see that, so this is continuum. So this will be my time delay.
Yes, but that means that the process is not stationary. That it has some time dependence, which is essential here.
Well, yes, but
Because if the
it's not exactly stationary.
because
That's
if
right.
it was
Yes.
radiating at the same rate all the time, there would
Yeah.
be no time delay.
Yeah, of course. So, but this is well known that all active galaxies are strongly variable. So if you look at the light curve, continuum
So
light curve.
there is some scale of the events in the quasar that is of the order of time.
Yeah, but this
1 year,
variability, this should be shorter, much shorter than this whole time delay, because the variability is connected with the Schwarzschild radius.
So the time scale is about 1 year. Since you measure time delay of the order of 360 days.
Yeah, and the variability is even, well, in days, but let's say days.
Okay.
So of course the whole theory is using a stationary picture to determine this thing.
So the essential thing are these changes.
Yeah.
in the-
Yeah, all AGNs do vary continuously. That's right. Quite significant variability, factor 2.
I have a question to expert of general relativity. I mean, normally if you construct an effective theory, then there are different terms, and phenomenologically it never happens that the coefficient in front of one of terms which are allowed by symmetry basically is exactly 0. It is always something. There are higher, smaller. So if you look at the Einstein equation as an effective theory, just relating objects of a well-defined geometrical properties, why do we expect that there is no cosmological constant? The coefficient in terms of the cosmological constant is exactly 0.
I wouldn't say that somebody expects that. It's just that you didn't mean that when people were just measuring gravity on the scale of our solar system.
It looks more elegant without cosmological constant.
Why does it look more elegant to you?
Because there are fewer
It's shorter, the equation is shorter, that's the simplest answer.
No, because there is another
Because
constant.
Albert said that this was his major blunder.
That's true,
some
but there
other
is
constants like C,
there is another constant.
No, but now they measure this constant and they have it, so that's it.
It was too small to be measured before, and now it's not.
The biggest
Yeah,
puzzle
because
is why is it so small?
Yeah, so the question is about the magnitude, right?
Vacuum fluctuations
And-
would be much bigger.
Well, if you believe in that, then we have this 120.
But I'm heading probably very strange questions. But if you really do have this dark energy, which is more or less uniform, dark energy, which is more or less uniform over the then there is a rest frame of that energy. which is a selected rest frame, right?
There is the rest frame of the...
Over black broad radiation. Now, that was the following question. Are these two rest frames the same, identical, or if, I mean, what will happen if they are identical? Question B, what would be the consequences if they are not like that?
No, lambda does not give you any reference frame. If you have cosmological constant, there is no reference frame.
Not preferred. Lambda does not prefer any rest frame. It's written in a covariant fashion.
So this kind of energy is not material in some sense.
Yes, it's a constant,
It
in
is-
the equation.
It's a constant in an equation.
Yes.
So it is completely, so it doesn't have this rest. So the answer was
No,
that there is no rest frame, so there is.
Yes, so this is why it's also annoying.
To przyszliśmy długą drogą. Bo ten Łukasz myślał, że te dwie rzeczy są dalej.
Yeah, well, I didn't think it, and the question is that if they are, then they either are different or there must be a consequence of it, right?
But fortunately or unfortunately, all fundamental theories are bringing constants into the description. Yes? The same
Well,
as
but
the-
if it is multiplicative constant, then it's somehow sort of better, and this is kind of additive, it just
some-
sits there on itself.
sometimes fundamental theories explain constants. That can also happen, and that's a big
By another constant.
bad
By another constant.
fundamental theory.
For
For example,
explaining alpha.
no, that was not explained, but for example, the magnetic moment of the electron was explained by the Dirac equation.
Yes.
So sometimes
Teraz inne stało.
And the H bar.
Yes, there is one which is not explained.
We need to introduce
So,
H bar to explain.
So the
H bar was there already.
Yeah.
yeah, but that's.
Well, so in other words, there's maybe still a challenge to compute lambda from something. Something
Lepiej byłoby nie mieć żadnych stawów.
But from what? It's a geometrical property.
Well, some people, when they develop those multidimensional models of universe and the brain things and whatever, then crossing one brain.
Yeah, but the brain has different constants. The brain has the constant with opposite side.
Żadnych
Then it-
Żadnych dostępów. To może zresztą.